there's a number being tossed around by scientists that should be getting a lot more attention than it is. 72%. That's the estimated chance that California will experience a major earthquake within the next 30 years. Not a tremor, not a small shake, a significant, potentially catastrophic earthquake. And it's not just one fault that could be responsible. The real threat comes from a network, a tangled, interlocking web of faults running through the state, each with...
If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment. Your feedback helps shape what we cover next, and you being here keeps the conversation going. Thanks for watching. See you in the next one.
Its own history, slip rate, and personality. The most well-known, the San Andreas Fault. But there's also the Calaveras, Hayward, San Jacinto, Elsinore, and many more, all connected in ways that make predicting earthquakes even more complex. California sits right along the boundary where the Pacific Plate slides past the North American Plate. That movement, about 30 to 37 millimeters per year, doesn't just disappear. It stores energy in the crust. That energy builds up over decades, even centuries, and eventually, it's released. That release is what we call an earthquake. This is a process scientists understand well. Strain builds, then slips. The hard part is figuring out when and where the next slip will happen. And that's where things get interesting and dangerous. Some parts of the San Andreas Fault are known to be actively creeping. That means they're slipping slowly, releasing energy over time, reducing the chance of a big quake. But other sections, they're locked, not moving, not releasing any stress, just holding it all in. That's a problem. Locked segments store elastic strain until it's too much and then they rupture violently. That's exactly what happened in the 1906 San Francisco earthquake and in the 1857 Fort Tejon quake. These weren't minor events. These were city-leveling disasters. And the same geological structures that caused those quakes are still sitting there, accumulating stress right now. At the junction where the San Andreas and Calaveras faults meet, things get even more complicated. Subsurface geology, including rocks like serpentinite, can actually promote slipping. That means rupture zones can transfer energy from one fault to another. In plain terms, one earthquake can trigger a second one nearby. Or worse, they can rupture together in a chain reaction. This is the kind of multi-fault event that hazard models are now starting to include. It's not just about one fault line breaking, it's about how multiple segments might link up during a single, massive event. These aren't just theoretical scenarios. They're built on historical data, rupture patterns, and the physical mechanics of how strain travels through rock. The Hayward Fault, which runs through the East Bay, hasn't had a major rupture in over a century. That's what scientists call a seismic gap. It's a section that hasn't released energy in a long time, and that silence can be just as ominous as activity. The longer it stays quiet, the more stress builds. The same goes for parts of the Calaveras and Rogers Creek faults. These aren't isolated cracks, they're part of the same system. Southern California brings its own set of issues. The San Jacinto and Elsinore faults are both known for their high slip rates. That means they're moving faster relative to each other, and accumulating strain more quickly. And unlike remote areas of the desert, these faults are dangerously close to major population centers. That puts millions of people, buildings, and critical infrastructure directly in the line of fire. And here's where the science really turns unsettling. Earthquake ruptures don't necessarily stop at fault boundaries. They can jump across faults. Stress from one quake can transfer to a neighboring segment, triggering a new rupture. That's why understanding junction points is so critical. They're potential ignition sites for domino effect earthquakes. Scientists also track how earthquake waves travel through different types of ground. The geology beneath a city can amplify shaking dramatically. Soft sediments, old basin floors, buried fault lines, they all play a role in how much destruction occurs when the ground moves. That's why Los Angeles, built over a complex basin, is so vulnerable. Even a moderate quake can turn into a long, violent event because of these underground conditions. And yet, despite all this detail, despite the decades of data and the advanced models, there's still one brutal truth. No one can predict the exact timing of an earthquake. What they can do is estimate the probability, and 72% over 30 years is not small. That number comes from probabilistic models that factor in slip rates, strain accumulation, paleoseismic records, and geodesy, meaning ground and satellite-based measurements that track how the Earth is literally stretching under our feet. These models are now so advanced, they account for single-fault ruptures and multi-fault, dynamic chain reactions. It's no longer just about one line breaking, it's about an entire system reacting in unpredictable ways. And yet, for all the science and modeling, One of the most important takeaways is brutally simple. Strain accumulates, and eventually, it has to release. Some faults rupture more frequently. Others are quiet for hundreds of years, then release centuries of built-up energy in one sudden jolt. Historical trench studies reveal this inconsistency. Some faults have characteristic quakes, regular, repeat events. Others are more chaotic. That unpredictability makes it difficult to prepare precisely. But it doesn't mean we shouldn't prepare at all. In fact, it means the opposite. The science shows us where to look. It tells us where the stress is highest, which faults are overdue, and how different segments might behave. It highlights junctions where rupture transfer is likely. It identifies how deep layers of sediment can turn mild shaking into a catastrophic wave of motion. But what the science can't do is force communities to act. That 72% chance, it's not just a number, it's a warning. A very loud, very clear one. It means there's a strong likelihood of a damaging earthquake within a generation. And if you're in California, you're living on borrowed time. That's not alarmism, that's geology. Every day, the Pacific Plate continues to grind past the North American Plate. The faults continue to store strain. And as scientists refine their models, map previously unknown faults, and simulate complex rupture chains, the message stays the same. It's going to happen. Preparedness isn't about knowing when. It's about being ready regardless. Retrofitting vulnerable buildings, strengthening infrastructure, planning emergency response routes, those aren't optional. They're the minimum. Because the longer we wait, the more strain builds. And when it finally slips, it won't care about population density, construction codes, or economic impact. It will simply move. And when it does, it could link fault segments together in ways we've only recently begun to understand. That's the real message here. Earthquakes are not isolated events. They're part of a dynamic system. A system that can evolve in real time as faults interact, shift, and release energy. That's why models now account for three-dimensional complexity, not just surface traces. That's why scientists are using everything from satellite geodesy to trenching to refine rupture recurrence intervals. It's not about predicting a single quake. It's about understanding how many different ways California could break and what that means for the people living on top of it. And right now, the odds aren't theoretical. They're real. That 72% probability isn't just floating around in academic journals. It's what hazard models are saying today, based on real data. And with every quiet year, the pressure increases. The system is loaded. So what can be done? That part's clear. The science is pointing directly at proactive preparation. Invest in resilient construction. Retrofit old infrastructure. Expand early warning systems. Run simulations. Educate the public. And above all, treat seismic risk as the ever-present threat that it is. California's landscape was shaped by earthquakes. Its future will be too. And whether that future is one of chaos or resilience depends entirely on how seriously we take the warning signs before the shaking starts. If this breakdown helped you understand the real risk California faces, share it with someone who needs to hear it. Leave a comment with your thoughts or experiences, especially if you've lived through a quake. And hit that subscribe button so you don't miss future deep dives into the systems shaping the world beneath us. Because one day, the ground will move. And when it does, what you know could be the difference between panic and survival. And here's the uncomfortable truth no one likes to sit with for too long. We know how this ends. We don't know when. We don't know exactly where. But we know what, and that's a seismic rupture so violent it could reshape entire regions of California. Not metaphorically. Literally. Buildings torn apart, freeways collapsing, power grids down, and entire neighborhoods unrecognizable within minutes. That 72% probability. It's not just a number meant to sound scientific. It represents a deeply researched, multi-layered risk profile based on decades of paleoseismic records, satellite geodesy, ground measurements, and modern fault modeling. And it doesn't account for doomsday hypotheticals. It reflects actual scenarios, backed by the real movements of the Earth under California right now. Let's break that down. The plate boundary that defines California's seismic character, the one between the Pacific and North American plates, is not a clean cut. It's messy, braided, and filled with offshoots. This isn't just the San Andreas Fault taking the spotlight. It's the Hayward. It's the Calaveras. It's the San Jacinto, the Elsinore, the Walker Lane, and the Eastern California Shear Zone. These aren't background characters. They're active participants in a system that doesn't care about political borders or whether we're ready. And while they might look separate on a map, in reality, they're often connected deep underground. That's where the real danger lies. fault interactions. We used to think of earthquakes in silos: one fault ruptures, then it's done. But updated hazard models now show that faults can link up. A rupture in one segment can jump into another, either instantly or through delayed stress transfer. That's why a 6.8 quake on the Hayward Fault could cascade into something far worse if it activates a neighboring fault with similar stress buildup. It's not speculation. It's physics. Take serpentinite, for example. This rock type shows up around junction zones, and it happens to make fault planes weaker and more slippery. It's the geological version of WD-40. If a rupture hits an area rich in serpentinite, it's more likely to continue spreading potentially across fault boundaries. This is why junctions like the one where the San Andreas and Calavis faults converge are so alarming. You've got a high concentration of strain, a history of large ruptures, complex subsurface conditions, and potential for linked movement. It's not just a rupture risk. It's a detonation waiting for a trigger. And if you think this risk is evenly distributed, think again. Some areas have been far too quiet for far too long. Sections of the Hayward Fault haven't experienced a major quake in over 150 years. That's longer than the average recurrence interval. And because this fault slices right through urban cores Oakland, Barkley, San Leandro, it doesn't take a massive rupture to cause staggering damage. Even a mid-sized quake here could level parts of the East Bay in under a minute. The Calavis Fault shows similar silence. And it's not silence we should find comforting. It's silence that points to strain accumulation. Quiet faults are often the most dangerous, because when they finally move, they release all the energy they've been hoarding. Further south, the San Jacinto and Elsinore faults pose the same threat, only now you're talking about proximity to San Diego, Riverside, San Bernardino, and a huge swath of inland development. And these faults move fast. Their slip rates are high, which means strain builds quickly. The intervals between large quakes may be shorter, but that also means they're under near constant tension. The way scientists quantify these risks isn't through guesswork. It's through paleoseismology, where they literally dig into the past, trenching fault lines and covering ancient rupture layers, carbon dating debris to map out when earthquakes happened. And what they've found is telling. Some faults rupture like clockwork. Others are wildly unpredictable. Some segments break every 100 years, others wait 500. But one theme keeps emerging across all this data. We are overdue. The fact that so many major faults across California are in seismic gap segments with no recent rupture activity should be sounding every alarm. That's exactly how it looked before the 1906 San Francisco quake, before 1857, before Northridge. Long periods of apparent calm followed by explosive destruction. And then there's the terrain factor, because not all shaking is created equal. It's not just about where the fault is. It's about what's on top of it. Sedimentary basins, loose soils, and filled land amplify ground motion. Think of seismic waves like sound waves. They bounce, they echo, and in the wrong conditions, they build. Los Angeles, for example, sits on a huge sediment-filled basin. When waves from a nearby rupture hit that soft ground, they slow down and grow in amplitude. That means more violent shaking, longer durations, and significantly more damage. Even areas that aren't right above a fault could feel like the epicenter. It's the same story in the Bay Area. Certain districts are built on old marshland, landfill, or soft fill zones. Those areas are disproportionately vulnerable. It doesn't matter how quake-proof your building is if the ground underneath it starts acting like a trampoline. Structural integrity won't save it. Now layer all of this with urban density, aging infrastructure, and socioeconomic vulnerabilities. You're not just dealing with a geological event, you're dealing with a full-blown humanitarian crisis waiting to happen. Bridges, water lines, power grids, hospitals, many of them were built before modern seismic codes. Even newer structures may only be designed for survivability, not functionality. That means in a major quake, they might still be standing, but they'll be unusable. And then there's the domino effect. If a major fault ruptures near Los Angeles, you're looking at freeway collapses, down communication networks, water outages, gas line ruptures, and power failures all at once. Emergency services overwhelmed. Evacuation routes blocked. Hospitals flooded with injuries and short on supplies. It's not panic, it's math. This is what the 72% probability is warning us about, not a hypothetical scenario, but a highly likely sequence of cascading failures triggered by real, measurable, and escalating geological stress. Preparedness isn't optional. It's the only line between disruption and disaster. So what does that mean in practical terms? It means retrofitting. Old buildings need to be reinforced. Infrastructure needs to be brought up to code. Utilities need to build redundancies. Emergency plans need to be updated and drilled not once a year, but regularly. It means education. People need to know their risks, know where to go, know what to do. Having a go bag, knowing how to shut off your gas line, securing furniture, it all adds up. It buys time. It saves lives. And it means policy change. Seismic safety isn't just a personal responsibility, it's a systemic one. City governments, utility providers, and regional planners need to act on the data. Because the science is clear, and the models are only getting more accurate. They show a landscape under pressure. They show fault systems that are active, interconnected, and primed for movement. And most of all, they show that this isn't some abstract threat. It's a real, defined probability with a number attached to it, 72%. You don't bet on those odds. You brace for them. And the reality is no one is immune. It doesn't matter if you live in the Bay Area, the Inland Empire, the Central Valley, or right along the San Andreas itself. If you're in California, you are part of this seismic equation. The plate boundary doesn't care about zip codes. Earthquakes don't negotiate. They don't delay for election cycles or infrastructure timelines. When the stress exceeds the strength of the rock, it breaks. And when it breaks, it's immediate. That's why the word preparedness gets thrown around so often. Because once it starts, it's already too late to prepare. In a matter of seconds, roads can fracture, power can go out, and emergency lines can jam. Entire communities can go from functioning to paralyzed. That's what's at stake. And yet, we still see denial. Cities dragging their feet on retrofits. Businesses skipping seismic upgrades. Renters living in soft-story buildings with no structural reinforcement. Schools that haven't been updated since the 70s. It's not a mystery. The vulnerabilities are mapped. The risks are documented. But action, it's lagging behind. The irony? The science has never been better. We're not in the dark. We know where the danger zones are. We know which fault segments are overdue. We know how rupture propagation works across fault junctions. The models are detailed, the probabilities are public, and the time to act is now. Stay informed. Retrofit if you can. Pressure your cities to act. Talk to your families about plans. And don't underestimate what that 72% is really saying. Because one day, not far from now, the ground will move. The question is, will we be ready when it does? Like, share, and drop a comment with how you're preparing or what questions you still have. And make sure to subscribe. Because the next time California makes headlines, it might not be for a warning, it might be for the one.